And thank you very much for inviting me to give this talk, and also Jean-Philippe and Jay for setting this all up, but also to the people of the CRM who made this possible very quickly. And thank you all in the audience for showing up to this talk. And okay, I hope to entertain you a little bit, and so that you don't start doing your email within 2 minutes, because I know that it's very tempting. Okay, I would like to tell you about some work I've been doing over the years with Jeff Williams, who's at SFU in Vancouver, on solutions to the Ohta-Kawasaki problem. So here's the outline of my talk. I will first tell you about the model. What does this equation, what does it model? Then I'll talk about the equations, all the parameters that are in them, and then I will first talk about two-dimensional results and results in 2 dimensions. Explain how the computer can help answer some questions there. I will talk a little bit about how we set up the computer-assisted proofs. It's not going to be an overview talk about computer-assisted proofs, but nevertheless, I will go into a little bit of detail, but not too much there. I'm not assuming you already know everything about computer-assisted proofs. And then finally, I will get to the 3D solutions. Okay, so let's go. So the Ohta-Kawasaki model, it is a model for Diblock copolymers. So these are very, very long molecules, where all these molecules, they consist basically of 2 pieces that are stuck together. So they have an A end and a B end, all the molecules. And all the B parts, they like each other, and all the A parts like each other, but A does not like B. But they have to be together, because together they are one molecule. So all the A ends of all the molecules want to be together, and all the B ends want to be together, but they cannot, because they have to also stick together in a molecule, and this leads to pattern formation. And that is what I'm particularly interested in. This is then the Ohta-Kawasaki model. It is some free energy. The material tries to, in the model, it tries to minimize this free energy here, and I will go into details in a moment. There are, of course, also other types of models, more mean field type theory models for these materials, but this is a mathematically much simpler model. Nevertheless, it's already hard to analyze and say rigorous things about this. Okay, so here is this free energy, and as you can see, there are 3 terms in it. So the U is the unknown. It is a scalar variable that is some kind of order parameter. When U is close to 1, then there are only A's there, and when U is close to -1, then there are only B's. And then, okay, so we take an integral here over the material to get to the total free energy. And so omega, you can think of this as some piece of R3 or some piece of R2 if you want to have a 2-dimensional model. And as you can see, we divide here by the size of the domain, so that we're really talking about the energy density. So that we can also compare different domains, basically. Okay, so then there are 3 terms, and the first 2, they are kind of the usual terms that you see in these type of energies. So the first term, it penalizes changes in U, so basically transitions. And the second term, it tries to put U equal to 1 or equal to -1. And then the final term is the special thing in the Ohta-Kawasaki model. It is a nonlinear term. A non-local term. Here's the, because this phi here, what is it? Well, it solves the Laplace equation over here. So it depends, phi depends on U everywhere in the domain. So it is not a local expression in terms of U. Now in this equation, we have another new symbol M, and this is the mass. So it tells you how much A there is compared to how much B there is. So if M is equal to 0, there's the same amount of A as B. But when M is larger than 0, then there's more A than B, and etc. Okay. Well, before me, so I will also tell you in a moment what the other parameters are. But first, the boundary conditions, because if you solve a PD, and already here I'm solving a PD, if I say that phi solves this Laplace equation, I have to tell you what the boundary conditions are. And I'm going to only take periodic boundary conditions in this talk. And of course, that will have to do with the fact that I want to make proofs and I have to choose boundary conditions that are not too difficult. But that's not really the reason here. It is because we observe that minimizers of this model, they want to be periodic. So that is the reason we're going to restrict our attention to periodic boundary conditions. Okay, so then I said there are two other parameters here. So gamma and sigma, well, they are basically just parameters that tell you how important the different terms are. So if gamma is really small, then this term is really large, and then it penalizes transitions a lot. So the transitions get sharper, when gamma becomes very small, and when sigma is large, then the non-local terms become more important. Right, so already when sigma is 0, you can see that this term is not there, and we are in a much more classical situation. I'll get that back to that in a moment. Okay, so and we'll look at 2D and 3D domains, starting with 2D just because it's easier to explain the pictures. In 2D, the situation is a bit simpler. But here are already numerical simulations in 3D to give you the motivation for what we're doing. Okay, so here on the right, this is a picture of experiments, and then there's already quite old results where on the left here there are numerics, but not for this particular model, but a more complicated model in fact. Well, if the resolution is nice enough, you can see that there are some nice patterns that you see in the different regions in parameter space. So this is basically parameter space. I will come back to that in more detail later, but you can see that there are different regions where you observe different patterns. And here more modern numerics with nice colors, but also more refined numerics. But they're numerics for this problem, the Ohta-Kawasaki problem. And you see all kinds of different patterns that you observe as minimizers, probably of this energy. These are resolved by Troxy, Pelletier, and Williams. And well, what you at least should take away from this slide is that everything you see here, it looks very periodic. It seems to be that even if you take boundary conditions that are not periodic, then the patterns that are formed, they want to be somehow periodic. Okay. So, okay. Something that I will not be able to explain why this is at all, but it is motivation for looking at periodic patterns. Okay, well, one way to do, for example, numerics for such a problem, how do you find minimizers, is using a gradient flow of the functional, and then there are many gradient flows you can choose. And this is, in this case, the popular choice, the h-1 gradient flow, because that gives you a partial differential equation as the gradient flow. So the energy itself had a non-local term in it, but when you take this gradient flow, then in fact you end up with a local equation, just a normal partial differential equation. And this is just a fourth order parabolic equation. And what I'm trying to show you here is the difference between what happens when sigma is 0. Sigma 0 means there are no non-local effects. And then it's really the Cahn-Hilliard energy. And there it has already been known for a long time what happens when sigma is 0 and you start with some really basically random initial data, then quickly A and B separate. So the U wants to go to 1 in certain positions and -1 in other positions. And then you see this coarsening of these, the blue bubbles here, basically. And when sigma is 0, that coarsening continues and continues until there's just one region with A in a sea of B, or the other way around. But when sigma is positive, when the A's and B's cannot really separate, that is what this non-local term models, that A and B, they have to be together in the molecule, then that coarsening, it stops at some point, at some length scale, that you cannot really predict in advance. And that depends on, that's basically intrinsic in the solution. You have to find it as part of the solution. Okay, so pattern formation you get then. And depending on the parameters, you will get different patterns. Okay, so the real problem that you would like to solve here, and this is not what we can do, I think, as mathematicians at this point, is the following. We want to take a big domain, because the size of the patterns is usually small compared to the size of the material, and then find the global minimizer of this, because that is probably what is going to be important. Now, you can nuance that a little bit by saying, well, maybe it cannot find anyway the global minimizer, so local minimizers are also important. But yeah, in the end, you think the global minimizer must be the really important thing. So let's try to find that one. Of course, always under the constraint that you know in advance how much A and B there is. You want to just fix the mixture of A's and B's in your polymers. But global minimization is difficult. Very difficult, because it turns out that there are just many local minimizers for many of the parameter values. There are also parameter values where there's nothing interesting, where you can find the global minimizer and it is just U equals a constant everywhere. This is not the case. Once you have found that, then of course you say this is not the case you're very interested in. But, okay, so but then for the case where there are patterns, there are often many local minimizers. So it already indicates it will be hard to find the global minimizer. And when you run gradient flow methods, then you also you get stuck a lot near almost local minimizers or near saddle points, and you then have to change time scales. And you can of course try to get out of local minima by adding some noise and all these things, but still it's hard to actually try to find the local or the global minimizers. Also because you want to do it on large domains. However, there is some asymptotic. So in asymptotic sense, some results are known. So when gamma becomes really small and m is close to plus or minus 1, then there are gamma convergence results that say things about what must happen in these limits. But yeah, okay, so that's only in the limit. Then there's of course some numerics that gives you indications of what you may expect but not a proof. And so this is here where we want to use the computer to at least prove some things for this minimization problem. So how could the computer help? So the computer is not going to help in the asymptotic regime where you have the gamma convergence results. There, in fact, computational results are very difficult. But in the non-asymptotic regime, where probably the material really is, right? It does not believe that gamma is really very small in the true materials. And in this non-asymptotic regime, we can try to prove the existence of certain periodic patterns. It does not, of course, imply that the global. Okay, so here I should maybe. One caveat, and I will not come back to this, is that of course we do not know that the global minimizer is periodic at all. Right? This seems completely out of reach to show something like that, except in some asymptotic limits maybe where you can do some things, but it seems very difficult to prove that. But okay, suppose the numerics really suggest that we only need to look at periodic patterns. So let's go and do that. At least let's try to do what we can do. So prove that really these periodic patterns that they exist. Try to optimize the length scale, because the distance between the spots that you saw in the pictures, or the distance between stripes and all these things that you don't know in advance, and you want to find the length scale that gives you the lowest free energy. free energy density. So once we have the periodic pattern, you would like to really prove that it is a local minimum, so that you know it's at least locally stable. And then when you have two local minima, you want to be able to say which one is better. So which one has lower energy. Okay, and these kind of things we can do using computer-assisted proofs. Okay, now I want to mention a little bit of earlier work. So before giving the talk, since this was the first talk in this series, I talked to the organizers and we agreed that I would not give a big overview talk about all the results that have been obtained. I could have easily spent 45 minutes on that, but so I'm only gonna mention a few results. So I apologize for all the people who are in the audience who actually worked on these type of problems and their name does not appear, okay? I apologize in advance. I want to just pick one type of result that I want to mention because it was really, the basis for our work, and that is other work on really periodic solutions to in 2 dimensions to a partial differential equation. In fact, a different partial differential equation, the Komoto-Szywaczynski equation. So this one, and in fact, these people, they looked at periodic solutions in time and space. So what I do today is I forget basically about time. I'm only looking at spatial periodicity, but nevertheless, many of the techniques are fairly similar. And so what they found are solutions like this that are here's time and then here's space. And so they found solutions that are periodic in time and space, so in all variables. And they had different types of approaches, and but there are 4 pairs of people, 4 duos who worked on this, and so that is at least what I would like to mention, that there is really and much more than this. There is work that underlies what I'm telling you today. It is not that we needed to invent everything to analyze this model. Okay, having said that, let's return to the Ohta-Kawasaki problem. And so here is some numerics for in 2 dimensions by Chokri, Maras, and Williams. And so now I'm gonna try to explain a little bit in detail what this picture represents. So parameter space here is 2-dimensional, and I said before there were 3 parameters, m, gamma, and sigma. But after doing some analysis, you quickly realize that there is actually a combination of parameters, gamma over root sigma, or some power of that, or something like this. That is a reduced parameter. There's only really 2 parameters, and one you can scale out. So this is why there's a 2-dimensional parameter space. So m was the mass ratio. So m equals 0 is the same amount of A and B. Just to recall. And then for many of these values of, and also here this axis, it starts at 2. So it would be, it would be in the newspaper, then of course you would say that is really bad axis here because you should start at 0. So it is a really bad axis, but everything below 2 is not very interesting because nothing happens there. And the only equilibrium is the uniform state where U is equal to M. Okay, so completely well mixed, so no patterns at all. Okay, so that's why it's not shown in the picture. And then for many parameter values, they just did numerics and tried to find what they thought was the global minimizer by just having a gradient flow and trying to speed up convergence and then kick it out of local minima and all these things. And then they found that for all these diamonds over here, there the global minimizer seems to be the uniform state U equal to M. And for all the circles here, they found that the global minimizer looks like a spotted pattern, so hexagonal spots. And for all the crosses, they found these stripes, which I would say is like a 1-dimensional pattern. If I take a cross section like this, and then it's just uniform in the other variable, so it's basically only depends on one variable. Okay, and then the black curves here over here, there are some parameterized curves that they chose as the probable boundaries between these different behaviors. I'm not going to talk about the dotted and the dashed dotted curves at all. So let's forget about that. Okay, so that is the numerics, and now of course you would like to prove some of these, right? As a mathematician, so this is what we set out to try to do. And in particular, we set out to try to prove the existence of this curve here. So this one, where what characterizes this curve? It's where the stripes, the best possible stripes that you can find, and the best possible spots that you can find where they have equal energy. So where you have the transition between the two different behaviors. Okay, so we're going to try to do that, and we'll, okay, I can already tell you, so that we can prove that there is this curve, and I will tell you in a moment how we do it. I should point out that there is this point here where everything collapses into the uniform state, and there's a bifurcation point. So there the computations will be hard, or at least you have to do something special to do it. But not going to spend a lot of time on it today. But here also you can do some asymptotics. Also you can really do some analysis by hand as well. Okay, so yeah, now we have to get away from the pictures and into formulas. And what equations do we need to solve? So, and what are the variables? Okay, so here we go. So I'm gonna describe everything in Fourier space because everything is periodic. So we'll talk about all the variables being Fourier modes. And well, for the stripes, these are really only one-dimensional objects, basically. They depend on only one variable in space. So these are, say, infinitely many Fourier modes for the stripes and infinitely squared Fourier modes, by letters of Fourier modes, basically, for the spots. And what else do I need to find? I need to find two parameter values that lie on the curve in my parameter plane. And I need to find two optimal sizes. I need to determine what is the best distance between the stripes and the best distance between the spots. So these are also variables. And what equation do I need to solve? Well, an ODE for the stripes, because now, although I started out with a PDE, it reduces to an ODE because it was only one-dimensional. A PDE for the spots, and well, there's some equation that describes that the distance between the stripes is optimal, an equation that describes that the distance between the spots is optimal, an equation that describes that the energies of the stripes and the spots that they're equal, and then finally, because I'm trying to find a curve of solutions, there's a technicality where I also have to have another equation to the so-called continuation equation that picks just one point on this line. Now to set this all up nicely, I have to do some change of variables, and I could of course go quickly over this and not tell you at all, but let me at least tell you a little bit of what is going into this. You would like to do proofs later on a fixed domain with a fixed function space. That is going to make life much easier. So rather than having the mass being equal to m where you don't know m, that's going to be annoying because then your space needs to be parameterized. And rather than having a domain that you don't know yet because you haven't determined yet the distance between the stripes, let's rescale so that all that gets fixed. So that we do. So there's a rescaling of space. There's a rescaling of u, so that the mass is now always equal to 1. And yeah, let's take this combination of the parameters that I talked about before I said gamma over root sigma. Okay, so it turns out that if you write down the formulas, everything looks a bit better if you do sigma over gamma squared. But obviously that is analogous. And then you end up with which equation? Well, this partial differential equation, which is again has this fourth order derivative in here that you have that we saw before, but and it is somehow well, it is just a Laplacian squared, but in these new variables. Okay, so that is what this delta L symbol really means. Okay, so that is now the PDE that we want to solve. And now we have to go to Fourier space. So let me go over what you do for the stripes, and then we go to the spots. Okay, so for the optimal stripes, okay, so we assume that things are periodic. So let's put in a Fourier series, and in fact, all the patterns look very symmetric. So let's only put in a cosine series. And then we plug that into the partial differential equation, and we get equations for the Fourier coefficients. And these are the equations. And here you'll recognize the Laplacian squared, right? Was k to the power 4 in Fourier. And yeah, the L1, it had to do with the distance between the stripes. And what else is there? There is this this u to the power 3 that we had before. It in a Fourier space, this is a discrete convolution denoted by these angled brackets. So these are the equations for the Fourier coefficients for the stripes. So it's an infinite set, obviously, for all k from 1 to infinity. And then, okay, here's the expression for the energy or the energy density in one dimension in Fourier's variables. And why am I writing this down? Because I need to find the optimal distance between the stripes. And the distance between the stripes is parameterized by this L1. So to find the equation that needs to be satisfied, I just take the derivative of that with respect to L1 and put it equal to 0. And that is the equation you need to solve to find optimal stripes. Okay, so this is what you get. So clearly, if you take the derivative of this, you get a -2 in front of it. So that is why there's a minus sign, and the half has disappeared. And also for the other terms. Okay, so this is what you do. And so let's go to optimal spots. There I'm not writing down the equations anymore, right? You now see what you have to do, and you do it now in 2 dimensions as well. And so we add these equations for all the coefficients for the spots, and you put in the energy balance, because on this line I wanted that the energy of this one was the same as the energy of that one. So you have 2 huge expressions for these things, and you put them equal, and it's another equation that you need to solve for. So these are the equations. And these were the variables and the equations. I try to more or less explain to you what goes into this. Okay. So now we need to solve that problem. And we're going to use a computer. And I will spend a bit of time explaining the methodology of how we do that for the people who have not seen that before. Of course, for some people, this is about the 10th or 20th time that they see this. So I apologize. So you can go and do email for 5 minutes and then get back later. Okay. So we want to solve, let's say a bit abstractly, a problem where we have fx equal to 0 in some Banach space. And we want to use a computer to do that. Okay, well, computer cannot work with infinitely many variables. So first we take a finite dimensional projection, as you always do when you do numerics, some truncation, a Galerkin truncation, or discretization, whatever you like. Well, yeah, basically whatever you like. Okay, so we have a finite dimensional truncated problem, and we give it to the computer, and we hope that we have someone, we can do it either ourselves, or we know someone who can do scientific computing and find for us an approximate solution of this truncated problem. Okay, so that's a bunch of floating point numbers, but since they represent a point in this finite dimensional subspace of the space I started with, I can also interpret that as a point in my infinite dimensional space. And now near this point here in my infinite dimensional space that I found, which was the approximate solution to the approximate problem, I try to find the true solution to the true problem using some analysis and with the help of the computer. Okay. So that approximate solution to the approximate problem is going to be x bar everywhere in the rest of the talk. Okay. So x bar is always the approximate solution. And then how do you prove that there is really a solution near this approximate solution? Or use a fixed point method that is not a very new result, I would say, right? That people have been doing for centuries. Okay, we're going to try to find a fixed point operator that we can analyze, and that will give us somehow that there is a true solution near this approximate solution. And then which one do you choose? Because there are many, many possible choices. And an obvious thing to try is to take Newton's algorithm and to try this operator. Because you know that that one has very good convergence, which means basically it's a very strong contraction near the solution. And that is a good idea, except that this operator is very hard to do analysis on, because although of course it is a linear operator that acts on f, this inverse, it itself depends non-linearly on x. So that is making life difficult and harder than it needs to be, because since the contraction of Newton's Newton iteration is so strong, I can give up a little bit of this contraction. So instead, and this is also what often happens numerically, you evaluate this Jacobian only in a single point and invert it. And then the obvious point to try to use there is the numerical approximation to the solution. Okay, so this operator you can take, but in practice, when you try to do the estimates, this is still a bit too difficult. So you take an approximation of this inverse of the Jacobian. And that I'm going to call A, and I will a little bit later on, I will give a little bit of an indication how to choose A. But in general, this A, well, it needs to be, of course, injective. It will have something to do with what you already have in the computer, namely the Jacobian or the inverse of the Jacobian that you have used in your numerics to truncate the problem. And then, well, it should be easy so that you can do analysis. Okay. Easier than the original operator, right? It's easier than that one. Okay. Now, before I continue and tell you what to do with A, I want to give two interpretations of what we're doing in terms of things that if you're not in computer-assisted proofs, you're likely to be much more familiar with. And that is that this is some form of a posteriori error analysis that you also see in numerical analysis. So we have already computed some numerical solution, and now we want to say something about how accurate it is. And the difference here with traditional a posteriori error analysis is that what we are after are explicit constants. We really want to know how close is the true solution to this numerical solution, if there is any. And the other thing is that we also we estimate the amount of nonlinearity, rather than assuming that the problem is almost linear there, which is the traditional thing to do. And another interpretation that you may be very familiar with is that this is very similar to what you do in classical analysis proofs, and nothing to do with a computer at all. It is just that there what you usually do is you invert some operator really with pen and paper. And the center of your ball, where do you center your analysis? Well, it's at some asymptotic expression of your solution, or some explicit formula for an approximate problem that you can solve. Okay. The big difference here is that our linear operator also lives partly on the computer. So you have a lot of floating point numbers that are involved in the definition of the linear operator. But really the idea is very similar to classical analysis. Okay, so what is this A? So of course I had a big problem with an ODE and a PD and lots of other extra equations, but let me try to explain a little bit more abstractly what A is for these Fourier problems. And to do that, since A is an approximate inverse of the Jacobian, let me first tell you the shape of the Jacobian, basically. So the Jacobian looks something like this. So this you should interpret as an infinite matrix. So it continues indefinitely in this direction, but only, let's say, only in one direction. Let's not do by infinite sequence, but just one infinite sequence. And let me assume that there was only an ODE and not also a PDE. But you will get the idea if you understand the thing for the ODE. Okay, so you see here that there's this thing here sticking out, and that's the first few equations. So there are a couple of equations that are strange. And these are the equations that tell you, well, the two energies have to be equal and the energies have to be optimal. These are two weird scalar, a couple of weird scalar equations. So not differential equations. Then here there's a few weird variables. These are the parameters. These are the strange variables. So not the Fourier coefficients, but the parameters that you still were, yeah, that you had to determine as part of the problem. What is m and what is the optimal distance and all these things. So what you see here, that is all the, let's say, this is the ODE and the Fourier coefficients of the stripes. And then it has a finite bandwidth here because there is only, in computing this, there is somewhere a convolution involved, but the numerical solution has only finitely many non-zero Fourier modes. So you only also see here finitely many non-zero Fourier modes in each column or each row, whatever you like. And that is why it has roughly this shape. Okay, so what is next? Because I'm going to approximate this, I'm going to throw away certain things in here when I do approximations. But part of this is going to be in the computer. Let's say this part over here. That's the part that after I do finite truncation, I have this part in the computer. And then there is a part here on the diagonal that I think is going to be important because for large Fourier modes, then the symbol of the operator is going to be the important thing. So the highest derivative. And so these are on the diagonal together with maybe some other stuff. And these are the things that I'm going to keep. So everything else in approximating this, I'm going to throw away. So I'm going to keep the part that is in the computer for all the low modes. And for the high modes, I'm only going to keep the linear part of the equation. So it's importantly, it captures the highest derivative. And now I need to approximately invert this. Well, this part I can invert by hand because it's diagonal. And in classical, in analysis terms, I'm just inverting a Laplacian here or a bi-Laplacian here, just in Fourier, so that it looks very easy. Okay. Yeah, so I just take the inverses. And then for this part, that is of course not easy to invert by hand, but it's a finite matrix. So I can ask the computer to give me an inverse or an approximate inverse at least. And that I plug over there. And then I have my linear operator A that I'm going to use. Okay, so roughly this is the idea of the type of computer assisted proofs that we're doing. This is how you choose the operator. Okay, so now we have the operator. Now we have to show that it is that it gives me a fixed point. So I'm going to use the Banach contraction theorem to do that. I have here still my point that I had from my numerical calculations. I'm taking a ball around it and trying to show that this operator, it is a contraction on this ball. And for that, 3 types of estimates are needed. And you do them by hand in combination with the computer. So you need to know how far does the center of the ball gets mapped away from itself. That estimate I do, and then I call that number that I get, I call it y. I bound the derivative of the operator at the numerical solution in the operator norm, of course, and then I find the bound and I call it z. So if z is smaller than 1, then it is at least a contraction at the numerical approximation. This is not enough. I need that it is a contraction on the entire ball. So for that, I also need to estimate the second derivative, right? And that is, in some sense, a harder estimate because it has to hold in the entire ball. So that estimate will depend on how big the ball is. So it depends on R. And you need to do this in the appropriate way. Take the norms in the appropriate way. I didn't want to discuss. Okay, so you do all these estimates, then you get big formulas that involve also all these floating point numbers. So you can determine y, z, and w only using the computer if you want explicit numbers for them. And then you're happy if this inequality holds for some r. Y plus z r plus a half w r squared is less than r. If that holds, then you have for that r or slightly smaller r, you have at least that, okay, the ball maps into itself and it is a contraction, so you find a solution. a true solution near your numerical approximation. Now, checking this inequality, you have to leave to the computer because the expressions for y, z, and w are so big. And now you also need to prove something. So this part of the calculation, it needs to be done with interval arithmetic. So in our case, with IntLab, which we used here, it's a MATLAB package. But this is the only part where I really need to use interval arithmetic because here I need to prove something. Okay. Choosing the size of the ball, it is always a little bit subtle because the ball needs to be large enough, of course, to include the solution. It cannot be too small. If you take it too small, then you cannot satisfy the inequality. But this is has been done many, many times. It's a Newton-Kantorovich type argument. In practice, it is a little bit more complicated, and I want to give you a little bit of the flavor of what is involved. Rather than showing you a lot of numbers, to illustrate that, I want to explain you the idea. Because we're working on a product space. We have Fourier coefficients for the stripes, for the spots, we have some other variables. So we have equations and variables that are really of totally different type. There are Fourier coefficients, there is a mass m involved, there's a product space. And I can take this product space and then say, well, that's a new Banach space. But then I need to choose a norm on X in some arbitrary way out of these norms on these much more natural spaces here. So let's not do that. And when you do not do that, you can still do the whole procedure. You just need to work on product spaces. And so instead of having the inequalities that we had here before, I now get, so say I have P different products in the spaces in my product, right? So I will get P estimates here for each of the P components. Finitely many. In our case, the problem that I just showed you, there were 6. There is going to be 6, but there are 6 estimates there. Similarly, for the derivative, I will get now P squared estimates, but this is all just bookkeeping. I was doing these estimates anyway. And for the second derivatives, I will get P to the power 3 estimates. Then, of course, I need to realize that R is now not just a scalar, but it is also P different values, because there should be R's in each of these different spaces. And X being in the ball corresponds to, yeah, basically it's a product now, right? So it's a rectangle. And the inequalities become these P inequalities, where there's obviously some linear algebra going on here, right? In all these sums. Okay, so now I get P inequalities in the end, and although it is not necessary, usually you take these W's to be polynomial, even often constant. So these things we call the radial polynomial inequalities. Okay, so we do all that, and then here are the results. So I'm not going to show you any of the numbers, but they're summarized here in the picture. So it's a very similar picture again, m and gamma over root sigma, and I've proven that there are these curves here, smooth curves, where the stripes and the spots have the same energy, and also here another curve where the spots and the uniform state have the same energy. Okay, it took 3 days to do this on a laptop, but it is not what I want to talk about too much. I want to compare to the numerical results that were there before, and this is when I overlay them. So you see that the proof actually it deviates a little bit here from the numerics before, probably because on the numerics before they didn't quite get the optimal distances between the spots. They probably didn't take a domain that was large enough. Anyway, the big difference, of course, is that these were proofs, and the other things are clever guesses after doing a lot of scientific computing. Okay. In the final 10 minutes, let's go to 3D. And then I'm gonna repeat part of that story. So it turns out that in 3D, it gets more interesting. There are more things that can happen. So this region and this region, we have seen these before. So these are really just one-dimensional solutions. And here we even see the spots, just that they now also depend on a third variable that they don't really depend on. Yeah, so now they're called cylinders rather than spots, but they're the same solutions. They're over here. But there are now 4 other regions where other patterns appear. So here we seem to have some kind of balls here, spheres. Of course, these are not really hard spheres because what you're looking at here are level sets of the solution. So just at some level set, it looks a bit spherical or very spherical. Okay, but nevertheless, if you assume that they're spheres, they have 12 nearest neighbors over here and here 8 nearest neighbors. So they're really different types of patterns. There's what is called the double gyroid over here. It's that picture, you'll see it again in a moment. And there's another state, so-called O70 state, that has a picture over here. It's another pattern, and it lives in space group number 70. That's why it's named that way. Okay. Now, we did not do quite the same as for the 2D problem here. We didn't want to find the curves again, because it was a lot of work already in 2D. So we're a little bit lazier. And just took parameter values and determined at parameter values many solutions, computed their energies, and found the one that had lowest energy. And then we also zoomed into the borders between the different regions and did things a bit more precisely here that we do not show in this picture. This picture is supposed to convey that we did a lot of points and then they colored them according to what we found as the lowest energy. Okay, so what goes in the 3D solution, 3D computations that does not really appear so much in what we did before in the 2D. The solutions have a lot of symmetry. For example, this double gyroid that you see here, it's called double gyroid because a level set has two connected components that are interlinked. It has a symmetry group with 96 elements. And if you take care of that, you can reduce the number of variables in your computation by factor 96. So that is a lot. And we also did prove in this case that they were local minimizers, and we compared energy rigorously. So let me spend a couple of minutes on each of these and then we're done. So reduce the number of variables. What is that? What am I doing? What are we doing there? Okay, let me explain in 2 dimensions because the pictures are easier. So suppose I have basically a double cosine series. I have reflection in X and reflection in Y. So symmetry group has, there are 4 elements. You can also always combine the 2 symmetries, the 2 reflections, I mean. In Fourier space, what do I have? Well, I have all these Fourier modes to start with, but some of them are not really independent if I have a symmetric solution. Just like in a cosine, AK and A minus K must be the same. So if I have here a mode, then that one is coupled to that one and coupled to that one by this reflection and then also coupled to that one. So out of these 4, there's only one that is really independent. And the same for this one also has 3 twins, say, that is linked to. This one has only 1 twin, right? Because under Y, it doesn't move. Okay, so in the end, these are not independent variables. So let's throw them away. And then we keep track of that all these green points, they have 4 friends or 3 other friends. So they're with 4 under the orbit under the group action. That is the formal wording, and there are 4 elements in the orbit under the group action for each of these points. And now for the orange points, there are 2, and the red point is on its own. Okay. So keeping track of all that, we can just do the whole analysis again, all the estimates. Just then, once you realize that this is a structure, it is not that difficult. In fact, this is the usual thing, right? Once you understand how the symmetry intertwines with what you're doing, then it is not really that difficult. Okay, but then you can do the same estimates again, but you have reduced the size of your problem by a factor 96. How about stability? So we had a problem where f equal to 0 was really putting the gradient equal to 0. So the derivative of f is the second derivative of e. So if I find the number of unstable eigenvectors, the unstable directions of df, of the Jacobian, then I found the Morse index of the solution. So I need to find the number of unstable directions of the Jacobian. at the solution. Of course, I don't know that because I don't have the solution, but I have the numerical solution. So I would like to find the number of unstable directions of df. And then argue that they are the same, but that is by a homotopy argument. By a homotopy argument, you can see that eigenvalues of df, they cannot, when I move from here to there, from the numerical solution to the real solution, then eigenvalues cannot cross. And in fact, that is not a difficult argument, because when I stay inside the ball, then t was a contraction. So the norm of this of the operator is less than 1, and then you see that df cannot have a 0 eigenvalue. Okay, so they are the same, the number of negative eigenvalues at the numerical solution and the true solution. But then even df and x bar I don't really have. I have a, but a is an approximate inverse of the Jacobian, and the number of negative eigenvalues of the Jacobian are the same as the number of negative eigenvalues of the inverse. And then another homotopy argument shows that a and this inverse of the Jacobian, they have the same eigenvalues. You could take a shortcut here somewhere as well, but okay. So that is what is involved. You just compute for a the number of negative eigenvalues, and that's the same as the Morse index after some homotopy arguments. Okay, let me skip this and go to the energy. Final thing, how do you compute the energy so nicely? Because it is very nice. You get very accurate energy estimates, and it is not difficult to understand why. So that's the final thing I would like to explain. Well, I'm going to use again that the gradient of E is F, and I want, for the numerical solution, I can just compute the energy very accurately. So I'm left with computing the difference between the energy of the solution and the numerical approximation. And I know that the solution is quite close to the numerical approximation. Okay, you may expect that the energy difference is also order R, but it is in fact order R squared. And that is because at the true solution, the gradient of the energy is 0, because the solution is a 0 of F. So in fact, it is very flat, the energy. Yeah, because you're near a stationary point. So in fact, the energy of the solution is order R squared away from the thing you can compute, the numerical energy. And then of course, now I say order R squared, but you can also get the constant there to make things explicit. Here's some nice pictures. That's all. We can also find some other solutions that look very nice and that we can prove are true periodic solutions. Some we can even prove that are local minimizers. These are called perforated lamella. They're kind of famous in the Ohta-Kawasaki problem, so that's why I give them a name. Some are local minimizers. This one is, we can never find this as a global minimizer. We always find a better pattern that doesn't look at all like this. And there are some other nice looking pictures that are solutions, but never local minimizers. So let me conclude. Then, using these computer-assisted proofs, you can get a lot of rigorous information about periodic structures of a model like this in 3 dimensions, including optimizing over the length scale rigorously. You can do this for any symmetry group. I showed you the one for the double gyroid that has 96 elements, but you can do that for any of the 230 space groups. Doesn't really matter. You can prove that things are local minimizers or that they are not local minimizers. And you can compare energies because you get very precise estimates for how large the energies are. It's one of the niceties of doing a variational problem. If you get some information almost for free. And then finally, this technology, basically, these methods, they also work for other problems. Not everything, because not all other problems are variational, of course. But we also used part of this to find solutions to the Navier-Stokes equations that are periodic in time and space. But that's a whole other talk. So I would like to stop here.
Thank you, JB. Very nice. Well, are there questions or discussion from the participants?
I have a question.
By all means.
I wonder what happens in this transition on this transition curve. So on the left of that curve, you have these the patterns in form of stripes, and on the right of this curve, you have these spots. And what do I have to imagine on the so there must be a transition between the two forms, right? When you cross that curve. So
Yes.
How do I have to imagine that?
So what happens when I cross the curve? I have a local minimum here and a local minimum here. One is stripes, one is spots. Yeah. And of course they're not coming together. Huh? So they're just apart and they just move a little bit. And then one gets lower than the other. So the other one becomes the global minimizer.
Ah, okay, so that's just the energy changes. All right.
Yes, just the energy changing. So there's not
there's no transition.
Some kind of local bifurcation there or something like this. It is really a global change in which one of my wells is lower.
Yeah, okay.
That is the only thing that is happening.
No transition between the solutions. No. Okay, thank you.
No.
And maybe Len had a question. Is that Leonard?
Yeah, that's me. Yeah, I was just wondering, when you say stability, do you mean stability of the associated gradient flow?
Well, yes, but they're also really local minimizers of the energy, right? So if you would take another gradient flow, there would also be stable.
But the type of gradient flow doesn't change the type of stability, but I suppose it does change the eigenvalues.
But maybe yes, but yeah, but of course the geometric picture is still the same. And locally, unless of course your space suddenly becomes so much bigger that there are really weird new directions that allow for instability. Yeah? But locally, the picture is just that it is a local minimizer of the energy, and which flow you take doesn't really matter, right? It's just
my question is basically, if you compute these eigenvalues that determine the stability of that gradient flow, if they are close to critical, you would expect these metastable states to be very persistent and maybe even show up in experiments. But then if the numerical value you get depends on the gradient flow you chose to study, then maybe it doesn't give you that information.
Yes.
Thanks.
But I mean, for stability, that seems very clear, right? I mean, it is really locally stable then for any. And then, yeah, and the size of unstable eigenvalues then really doesn't play a role, right?
Okay.
Yeah. But indeed, if you're at a metastable state in the sense that you're near a saddle point, then of course you could try to change your flow so that it moves away faster. Mm-hmm. Yeah.
I think Jason has a question.
Yeah. So this goes back to the first question with regards to the states. So there's no transition between the two, say the spots and the stripes. But do they always exist? Are they always there? Or are they disappearing in really complicated bifurcations?
Oh, they do disappear. Yes. And
okay.
So probably these other curves over here, right? They have something to do with things like that. And they might not disappear in very complicated bifurcations. They might also just disappear into the uniform state, for example. So they might actually be bifurcations that you can really track. But then they're no longer the global minimizer where that happens. So, yeah.
Okay, thank you.
Sure.
Michael, you had another question?
Yes,
Michael,
if I may.
yes.
So, yes. Thank you. So my other question is, you said near the beginning, in order to motivate the periodic boundary conditions, you said that the solutions want to be periodic. And so how shall I interpret this statement? So are you saying that you, please?
I take a big domain and maybe I just put 0 on the boundary, right?
Okay.
Or normal boundary conditions. And I take initial data and I let it run. So this is also, well, now I have to, maybe I can even go back and, oh, no, that doesn't work. Okay, yeah. Okay, maybe I go to that picture because that was actually exactly what was done there, right? In fact, there were periodic boundary conditions here, but that is not so relevant. So, but what happens is that, yeah, even if you take other boundary conditions, then well, when you're not near the boundary, then it starts to look like there are all these spots and they're all at regular distances from each other.
Okay, so, but
so in that sense, they want to form a periodic pattern.
Oh.
And then, of course, there may near the boundary may be some discrepancies, or it may have take a long time with the rearrangement. But if you take a big domain, then in the middle, it starts to look very periodic.
So in the principle,
kind of, yeah.
In principle, could you make that so some kind of conjecture? So you could make say you take the domain bigger and bigger, composed of these little domains of which you regard as or hope for being periodicity itself, bigger and bigger. Take the energy and then divide the energy by the number of little domains you have taken for that bunch. And then the limit is would create a periodic solution, something like that.
Okay, so myself, I'm not completely familiar with that, but there are formulations that make that precise. And in fact, in the gamma limits, it's some of these gamma limit arguments, when the capital gamma limit arguments, but where little gamma, it goes to 0. There they also prove something like that, that there's some kind of weak form of periodicity that is the limit that you obtain in the limit, in some asymptotic limit.
Okay, I can imagine, yeah. Okay, yeah. Thank you.
Excellent. Any other questions?
Can I ask real quick? And Berg, you are testing when you're talking about the period. This is a local optimality, is that correct? Right?
Sure. Yeah.
Right. So is there any sign? Has anyone seen something that this can, like the optimal period, might change? So, for instance, you could look at within a range, or you could have harmonics bifurcating, like spatial harmonics, spatial period doublings, things like that.
Yeah,
that's something that's of concern in the system, or.
Yeah, that may happen. Yes. But of course, we did not. That is not something we compute. We did it a couple of times, right? You take your solution, you double the domain, and you see whether it's still a local minimum, right? Because that you can still again do it, and okay. So, but we did not. Do a thorough investigation of that. But yes, and then you have symmetry breaking. So yes, there are definitely, we also saw some of those bifurcations. This is anecdotal in some sense, right?
I guess you could sort of do a compute, in theory, you could compute the Bloch wave spectra, right? But
yes,
Right. No, just curious. So people haven't seen something like that would suggest you must test this or so in this particular system.
No, yeah. So for the global minimizer, it doesn't seem to influence that. But yeah, we also looked at a lot of other solutions, and there it definitely happens that these things. So maybe in other models, so in fact, that might be important. Yeah.
Thanks.
I think Jean-Philippe has a question.
Yes, so I was just wondering, so you did all of these proofs were all done on a laptop? on your basically on your laptop?
Yes.
Or you had, okay, so
Oh, no, no. Well, I think we used a desktop at some point.
okay, and then because you
there were so
divided-
many points, so otherwise it would take so long. Yeah.
Okay, so Jeff.
But it was
will
not
have-
I mean, it was not a supercomputer or anything like that, or a big cluster. It was just, yeah.
And then there, did you reach a point, because you divided by 96 the number of elements, which is great, but did you reach a point where you pushed it to the limit so that memory, I mean, when you inverted this finite dimensional matrix, then it became like a
Yes.
memory issue?
Yeah. Okay, so yes, of course we can, that is nice. With these computer assisted proof, we can also always push it to where it fails, right? So, oh, I didn't want to do that at all. That's okay, let's see. Okay. Maybe this picture is the right one, huh? So we stop here at gamma over root sigma more or less 5, right? But when you go up with gamma, then you already know the transitions will become sharper and sharper. So you will need more and more modes. Also, when you do numerics, you believe that you need more and more modes. Of course, you're trying to use as few modes as possible. That I think is the whole point of this. You're trying not to use so many modes, but now you need more and more modes. So then, yes, you run into at some point some difficulty, and it depends on the solution, right? It may be that here you can go, well, in part you can go up further because the solution itself requires fewer modes, and in other parts where the solution it requires more modes. So yes, and it's very easy to push it where it fails by just continuing up along the vertical axis here, anywhere. Yeah.
Okay, so the bottleneck is really memory.
Yes.
Okay, yeah, it's good to know. Yeah, so Jeff said that everything ran on a small laptop. Eventually, memory is the problem.
Yes.
Mm-hmm. Okay, thank you.
Michael, you had another question?
Yes, thank you. So I have a question concerning the model itself. So as you wrote down the energy at the beginning, then there was this term phi, so there was U and phi, and then for phi we have a Laplace or Poisson equation with U minus m on the right hand side.
Mm-hmm.
So in principle, one could also try the whole thing as a second order system for U and phi, and instead of making it a fourth order scalar equation. Do you expect any advantages or disadvantages, or has anybody else looked at that thing as a system? So that the advantage, of course, we have only second order.
But it is a disadvantage to only have second order. Having fourth order is better because you get quicker decay.
Okay.
And a scalar equation is less bookkeeping than a system. So in both aspects, it is easier for these proofs and also for the coding to write it as a single equation.
Okay.
So that is a conscious choice, in fact, to try to do that always when you can.
So the reason is that you treat this this problem in Fourier space, and therefore you get a higher dominance of the eigenvalues in the fourth order system. So that's so to say.
Yeah. Well, I think that is okay. And there's also a Laplacian in front of the nonlinearity. So in the end, probably that doesn't really matter so much, but it also saves a lot of bookkeeping not to have to work with the system and having a scalar equation. So coding is just easier. Of course, the regularity cannot really get better by writing it as a system rather than a scalar, but yeah.
I was thinking of analytical aspects where fourth order problems are certainly not easier than second order.
I agree.
But
yeah. So if you do, if you're not in Fourier, then it might be, and you want to write down Green's functions and stuff like this, then it may be better, in fact, to write it as a system. I agree. Yeah.
Okay, thank you.
Any other questions? Well, if not, I'd just like to thank everyone for showing up again, and thank JB again for speaking. And I hope we'll see a lot of people again next week for the talk of Jonathan. And